Aloha, Richard Halverson here. This is ITS228, and today is March 23rd. Let me share my screen. And 228 syllabus. Something's wrong with it. All right, well, so we are in, we're going to talk about heaps and trees today. Last time we talked about, actually, we're not going to talk too much about trees, but last time we talked about balanced trees and ABL trees and so on. And I owe you a assignment 5. I've adjusted all these. I'll give you an assignment 5 tomorrow, and I still have to get the grader project or the grader thing working for AutoGrader for assignment 4. I'm just about ready with that. So anyway, today I'm just gonna talk about the chapters, and I'm gonna so you understand what heaps are and how heaps are my favorite data structure, and they're trees or binary trees, but it's really easy to manipulate them. And so the assignment 5 is going to have have some sort of ABL tree assigned part to it, and then it's going to have probably a priority queue part to it, and you'll implement the priority queue as a heap, and you'll see how it's very easy to do that. So let's go to so I'm not going to talk about any of the assignments more than that today in this period. If you think you can go through chapter 8, go through assignment 8, and heaps are a pretty simple concept. So you may just be able to go through the sections of chapter 8 without having to watch the video. I'm not sure if I'm going to have too much more enlightening things to say regarding heaps, because they are actually pretty simple. All right, so the heap concept is you have a binary tree, and the property of the binary tree is that a node is, let's say it's a max heap. A node is greater than or equal to each of its children. Okay, and each node is a heap. So by inference, the top node is in a max heap. The top node is the largest node, the highest key node, and then each child is also a heap. So all the way down are heaps, and so and it turns out that if you're just always looking for the biggest one, and you want to consume the biggest one, and then reheap it, so you know what the next biggest one is, it only takes O of n log n, or O of log n to reheap it. And same with adding something to the heap. It only takes O of log n to add a node to the heap. All right, and so we will talk about a heap sort in here too. There's another nice property about it, heap, and that is it's really easy to envision it and manipulate it as a binary tree, but manipulate it the abstract data type as a binary tree or a heap, but the actual underlying implementation doesn't have to be nodes and linked lists. It can just be an array, because a heap is always a complete binary tree where all the nodes if you were to represent the nodes as an array, they're all, you only need as many slots as there are nodes in the heap, basically. And you'll see what I mean here. All right, so here's an example of a heap. 98 is a heap, or I mean, this one on the left here is a heap because the top node is greater than or equal to its children. Same with this one. This is a heap. This is bigger than, this 50 is bigger than 49 or 47. 22 is bigger than 14. 98 is bigger than 50 or 22. So so go through this to make sure you understand the concept of a heap. Let's look at this binary tree. Is it a heap? Well, nodes are always, the bottom nodes are always heaps. How about the first node that's not a leaf node is 55, and that's not a heap because 60 is bigger than 55, so it's not a heap. Let's see, 44. This 44 is a heap. 77 is not a heap because 55 is not a heap. All right, so 33 violates the max heap property due to being greater than 22. No, that's not true. 54 violates, no, it's not. That's not true. 60 violates the max heap property due to it being greater than 55. Yes, that's the problem. Actually, it's, yeah, right. Okay, I'll just put true. A max heap's root must have the maximum key. Maximum key, yes, that's true. All right, so and so here's how we insert into a max heap. Okay, so in this case, what we do is we add the node to the first spot in the tree, doing a breadth first search from left to right, the first open spot, and you insert the node there, and then you reheap. Okay, to reheap, you only have to percolate up that node that you just inserted. Okay, so here we'll see how this works. So we're going to add 85, and so we stick it down here at the bottom. Okay, and that's the first spot, and then let's go, and then we need to percolate this thing up. See, so we percolate that, and so we're done. So we percolated 85 up to the 80 spot. So that's what this looks like, and then we don't have to percolate anymore because the 88 is larger than 85 and 33. All right, and then so next we're gonna remove 88, and so that goes away, and we replace it with 80, and then we percolate that node down. See, so this thing did all three steps at once. And so with these heaps are designed where you would it's the top node that you're interested in, so it's the maximum that you're interested in. A heap sort, we'll see later, is very simple because you just pull off the top node, stick it over there, reheap, next one, keep on doing that, and each one you keep pulling off is the next highest one as before, and you end up, you pull them all off in order, you reheap them each time, and so the algorithm takes O of n log n because it's n times you have to pull off the top, and it's log n each time you have to reheap after that. So this shows both removing and inserting, and we use this percolating thing. And as you might imagine, the percolate function is quite simple. You're just swapping nodes as you're going up. When you it's not like an AVL tree where you have to like rotate. If it's out of order, you have to rotate these nodes. That's it's quite a bit more difficult. All right, so this makes sure you understand what the concepts here. The great thing about it is, inserting and deleting just takes O of n log n, or just takes log n. It's just the height of the binary tree. So if there's 1,000 nodes in the binary tree, that's 10, the height of 10. So given n nodes, what's the height of a max heap? It would be this, and log to the base 2 of n. Operations keep the tree height. Operations keep the tree height to a minimum, and each level is filled left to right. And so go through these to make sure you understand these. Given a max heap with n nodes, what is the worst case complexity of an insert, assuming an insert is dominated by swaps? So it has to put that in there because swaps is the thing we're counting. And so that would be log this one. Everything's log here. Okay, a min heap is like a max heap, except for the top node is the minimum. It's the smallest node. It's small. It's smaller of its children. Both of its children are larger or equal to a parent. And so this is an example of a priority queue right here, where if the smaller number is the highest priority, in other words, if 1 is the highest priority and 100 is lower, you can use a heap to do that, to keep track of that. And so all the agents are busy, and as soon as one becomes available, you pull off the top one because that's the highest priority. It's a min heap. And then right after that, you reheapify. You would take the bottom, the one at the end, and stick that up at the top there, and then you percolate down, and you would end up with the 62 right back at the bottom again, and 62 goes up here, and then it percolates down. I guess it percolates down this way. All right. So anyway, make sure you understand this. Let's take a look at this one here. Select all valid heaps. Let's just do the first one. You start with the first inside node, which is 70 here. And is 70 a heap? Okay, the leaf nodes are always heaps because it's just where they don't have any children. You start with the first node that's got a child, and that would be 70. We're going like this. So is 70 a heap? Yes, it is. Is 68 a heap? No, it's not, because 97 is bigger than 68, so that's not a heap. Is this a heap? No, because it's not a complete binary tree. But still might see. Is this a heap? No, this is not even a heap because it's 50. Okay, no, that's not one. Is 58 a heap? Yes. Is 91 a heap? Yes, it is. So I'm going to check this one. And what's the first inside node? It's 40. Is 40 a heap? Yes, it is. Is 51 a heap? Yes, it is. Okay, very good. So this explains that you can use arrays it's great. You use an array as an underlying data structure to store the heap. In Python, we're talking about using a list and being able to just use the indexing of a list, and not and really not anything else. We don't have to traverse or anything, or keep track of pointers or indexes that are children, because it all fits nicely into a nice complete binary tree. As however many elements are in the heap, that's how many elements are in the list, and it's indexed, and you can refer to children by using a formula on the index, and you can refer to parents using a formula on your index. All right, so heaps are typically stored using arrays. given a tree representation of a heap, the heaps array form is produced by traversing the tree's levels from left to right, on top to bottom. So this is the top level, and then there's two after that, right? So it's this one, and then it's 4 after that. This one, this one, this one, and so on. So this is the first one. This is the second one. This is the third one. This is the fourth one. This is the fifth one. This is the sixth one. Seventh one would be right here. The eighth one would be here. The ninth here, and so on. So you can see it's a nice compact binary tree. And so a max heaps array form is produced by traversing levels left to right, top to bottom. When 63 is inserted, the percolate up operation happens within the array. So 63 is inserted. Okay, that's that. We're seeing the end result here. So let's just click through this and see. So we start out with it. We're going to fill in. We're filling in the tree. Okay, so we filled. Okay, so this is actually how we represent this. This is the array form of this. And when we add 63, then we exchange 63 and 43 because we're percolating up, and that's all the farther we have to do. So we these exchanged. So you can see the parent of 44 is 5 divided by 2, and 5 divided by 2 is 0. We'll get to that later. All right, so I'll wait till the book explains those formulas before I try to jump ahead here. Okay, so so here we're matching each of the heaps with, this is what the storage array looks like, and I'll do one of them here. Okay, so is this a heap? Yes. Is 19 a heap? Yes, it is. Is 42 a heap? Yes, it is. Is 57 a heap? Yes, it is. Okay, so it should be 57, 42, 19, 13, 6, 7, 5. 57, 42, no, 57, 42, 19, 13, 6, 7, 50. Okay, so this A is this one. All right, so you can do the rest of them. Okay, here, this talks about parent and child indices. So because heaps are not implemented with node structures and parent-child pointers, traversing from a node to parent or child, node to parent or child nodes requires referring to the nodes by index. Okay, so the table here shows the parent and the child index formulas for the heap. So here's the node index, and that would be, I guess, the parent, the top node, the root node. And then if the node index is 1, then it's just got one parent. If the node index is 2, it's still 0 is the parent. 3 is 1, and so on. So this shows the parents. It's this. It's I minus 1 over 2. It's the floor of that, which is the highest integer less than this or whatever. And for the children, this is the left child. That's easier to think of. This is the left child, and this is the right child, if there is one. So we have 2 times the index plus 1 and 2 times the index plus 2. So we have this is the node, and if it has children, it has 2 times the index plus 1, which is 6 plus 7, and 2 times the index plus 2, which is 8. So these would be the children nodes, the index of the children nodes, if there are children nodes. All right, so what is the parent index for a node index at 12? Well, it would be 12 minus 1 is 11. Divided by 2 is the highest index less than then 11 divided by 2, which is 5.5, is 5. So I would say the answer is 5. All right, there you go. So you can do the rest of them. This is the percolate algorithm. And so this is percolating up. And here we're using nodes. Oh, no, we are. No, we're not. We're using indexes. Great, we're using indexes. Okay, so this is good. We can, you know, here we have swap this with this, and in Python there's a nice swap operator, swap operation. In every other programming language, you have to use it. It takes 3 statements, and you have to use a temporary variable. But anyway, so this is the percolate up and percolate down algorithms, and you see it just percolating up. It checks to see if you are it checks to see if you are greater than or equal to your parent. If you're greater than it's only if you're great. Okay, it checks to see if you're greater than your parent. If this checks to see if you're less than or equal to your parent. If you're less than or equal to your parent, you're done. So this is just return. If you're not less than or equal to your parent, then you're greater than your parent, and then you want to swap with your parent. You want to swap. You and your parent have to swap places, and you do that. And this is a iterative version of the percolate up algorithm. You could write a recursive version of it. I'm not going to have you do that. These just do the iterative version. That's fine. I actually do have you implement this in the assignment that I'll talk about tomorrow. All right. So and this is percolate down. So when you pull a node off the top, then you take the very last node down at the bottom and put that up at the top, and then that's got to percolate down. And this percolate up is used when you add a new node to the heap. You stick it on the very bottom, and then you percolate that one up to its proper place in the heap. Max heap percolate up works for a node index of 0. I would say no, because you're already at the top. Percolating up on the root is a valid call, although the algorithm will terminate immediately once the node index is checked for the first. Okay, so it works in that it accepts it, but it's not going to do anything. So basically, I was wrong. And their point is that even if you call this function with a node index of 0, the first thing that happens is it checks to see if the node index is greater than 0, and if it's not, then it just falls through and it's done. So it's done percolating. So anyway, trick question. Okay, so let's try this one. What is the above max heaps array form? Well, I would say that it's 86. This is so easy. 68. 86. 44. 24. All right, you can do the rest. What does the next one look like? What are the parent and child indexes for the node at index 13 in a binary heap? Oh, they've introduced us to a new term, haven't they? Well, that's a binary. You know what a binary heap is. 13. Well, it would be what's the parent index of 13? Let's go back up here. Parent. 13 minus 1 is 12. Divided by 2 is 6. So I'm going to say 6. And what is the left child index? Well, it is 13 times 2 is 26, plus 1 is 27. So it's 27 and 28. 27. Wow. 27 and 28. Is that right? Wow. Oh, there you go. Right. Well, I think you can do the rest of them. Okay, here we talk about Python heaps, or implementing heaps in Python. And so we are using lists. It's a list, even though we call it an array. Max heap tree grows from left to right. A new level is added only after the current level fills up completely, because the tree is nearly full with at most one level completely not filled. An array implementation is efficient. So the array implementation means that the root is always at index 0. And the index of any nodes, parent and children, can easily be calculated, as we see here before. Yes, that's exactly the same formula as up above. Note that the // operator is used in the parent index calculation, performs integer division. Right. Well, I'm glad they told us that. All right, so this is what the max heap class looks like then. It's just an array. And this is the percolate up function. Okay, so let's do one of these. The max heap is represented by the array that. Calculate the requested node's index. If the requested node does not exist, enter none. What's the parent node of 9? Okay, this is 9. And so this is the root. This is the root's children, the left child and the right child. And then we have this, of the left child, we would have a 7 and then a 9. So this is the right child of 10. What's the parent of node 9? I would say, well, the index 0, 1. So 1. That's the index. Yes. There's that double slashes again. The left child. So index they're asking for. What's the left child of node 17? So this is the right child of. Okay, so this is the right child of node 22. This is the left child of 10, the right child of 10, the left child of 8, the left child of 17. This is the left child of 17. The index of 8 is 0, 1, 2, 3, 4, 5. So this is 5. Methinks. What is the right child of node 9? Okay, so well, I should just be able to use the calculation, use the formula. So node 9 is 0, 1, 2, 3, 4. It's 4, index 4. What is the right child of index 4? Well, the right child is 4 times 2 is 8, plus 2 is 10. So I'm going to say 10. What is the right child of node 9? Node 9 is 0, 1, 2, 3, 4 is the index. Hold it. I said right child. Oh, so it's not 10, it's 11. I did the left child. Still wrong? Okay, let me do this again. 0, 1, index. 0, 1, 2, 3, 4, and we want the right child. So its index is 4. Four times 2 is 8. Plus 2 is 10. And 10 wasn't the right answer. Well, I'm just going to see what the right answer is. Oh, none, because there is no node at 10. 10 was my answer. The right child index is 10. Yeah, right, 10. It's an odd number. The left child is always it's an even number. The left child is always the left child is always an odd number, because this is going to be an even number. Plus 1 to make an odd, and an even plus an even is an even. So the left child is always an odd number, and the right child is always an even number. So that's the index. The index is 10. That's correct. It's the right child is an even number, but the trouble is there's no node at index 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's no 10. So that was why I got the wrong answer. This is the right answer. None. All right. So here are the heap percolate methods for in Python, and we have here we're percolating up, so we're at some node down somewhere, and we got to figure out what the parent is, the index of the parent, and then we check to see if the index of the parent, no, this is the index of the parent. It checks to see if the node is less than or equal to the parent. If the node is less than or equal to the parent, we're done. So we can just return. Otherwise, we have to swap the node with its parent. And here it is using this, the way you would do it if you didn't realize that you could use the swap operator in Python. But you can do that. It's this comma this equals this comma this. And you just do that in one statement, and you don't need these temp things. But in any other language you would. And then this sets the node index to its parents, and then so after you've done the one percolate swap, you got to see if you got to do it again with the parent. While the node index is greater than 0. If you get to 0, then you're at the root anyway. And here's the percolate down. So for percolating down, you've just popped off the top, and you take the one at the very bottom, or the last one in the array, the last index of the array, and you put that up. You put that value up at the top in index 0, and then you percolate down. So while there is a child, see, that's I got caught by that one in these here. I got caught by this one. While there is a child, then check to see if you are smaller than. Check to see if you're smaller than your child. While I is less than 2, and here you're checking each child. There's two children 0 and child 0 and child 1. It's added to this, starts out with I equals 0. And so here you're checking its max value. Oh, you're finding the maximum of your children. You're finding the maximum of your children. And that's what and that's how you percolate down. Is that how this works? Anyway, I'm going to have you implement this. Okay, so max heap array. Here you have a max heap array where this one is bigger than these two, and this one is bigger than these two, and this one is bigger than these two. No, it's not. Wait. This one is supposed to be bigger than. It's not. How many swaps are done when percolate up is called on the last index? Okay, yeah, that's a thing. So percolate up has got to be called. How many swaps? Well, 14 is gonna 14 will swap with 8, and that's it. 1. The parent is 8. Value is 8. Because 14 is greater than 8, then the two nodes swap. And now 14's parent is the root, which is 15, which is okay. So you don't have to swap. Here's another max heap array. How many swaps are done when percolate down is called on the first index? Okay, so this was just put there. I don't understand how that could have been put there because. Okay, so how many swaps are done when the percolate down is called on the first index? Oh. Okay, so this is going to. I don't. This is a max heap array. All right, I say 0. No heap violation exists, so the root at the root, so no swaps are performed. Okay. During the percolate down, a node's key is smaller than both the left and the child's key. And here, this asks the exact question that I was unsure about before, and it is whichever child is larger. So that's, I think that's the answer. Is that the answer? Yes, the swap must occur with the larger child, or else a max heap violation will occur. Oh yeah, oh of course, because it has to be done with the larger child, because when the exchange takes place, you're exchanging the one that becomes the new parent has got to be bigger than the child that was not swapped with. So of course that makes sense. Okay, here are the insert and remove methods for Python heaps. When you insert, you just append the value onto the end. That's going to stick it at the very end of the array, and that'll be the first open spot. And then you percolate up. This is the index of the value you just appended, and so that's the index of the node that you're going to percolate up. And removing is going to grab off the max value, or the top one, and then it's going to put the it's going to pop off the very bottom one, and it's going to put that one up at the top right here, and then it's going to percolate that index down. So go through these participation activities, make sure you understand them. And here's the heap algorithm. I'm going to have you implement this heap algorithm because I'm going to have you start with this. I'm actually not going to have you implement heap sort, but I might have you implement heap sort. I might have you implement heap sort sometime before the end of the semester, but so let's go back up to this for a second. And you see that this heap program that you're going to implement on your server is just a simple, there's the heap class, and it has the percolate up method, a percolate down method. That's all it's got there. It's got an insert, it's got a remove. And here's where it starts out, where you create, you have this class called max heap, right? You have a class called max heap, create an instance of it, and then you insert them into the heap. You use the insert method to insert these values one by one into the heap, and when you're done, each time you insert it, it inserts it, and to make sure it stays a heap, reheaps to make sure it remains a heap, and then this thing removes it. It probably displays it out. It ends up displaying it out in sorted order, it looks like. Anyway, so you can see that. And I'm going to have you start by implementing this, and then I'm going to have some ways to test it and so on. All right, and so this shows the heap sort algorithm, and this is my favorite O of n log n sort. It's great. You can use an array. It doesn't take any more space. Excuse me. So go through this and make sure you understand it. It's basically just you take the top, take the bottom one, stick here. Let's go through this. So this is what the heaps. Okay, that is the creation of the heap. That's how you start out with an array and you heapify it. When you start heapifying it, you start with the first inside node, and that would be this, right? This is the first inside. It's already heapified, but this is the first inside node, and you let me do this again. So here we're, yeah, okay, stuff. So this is going one, now it's going to pull off the 73, and it's going to take the 20, it's going to pull off the 73, put it where the 20 is, and the 20 is going to go where the 73 was. So it's going to, the 73 is going to go where the 20 is. So basically these two are going to exchange. That's this one and this one are going to swap, and then the index is going to increment. So in other words, this one and this one swap, and then the 73 disappears because the index is decremented by 1. You see that. See, then it's got to, each time it goes, it's got to percolate down, and then we finish. The array is sorted. All right, so make sure you understand these participation activities. This is the heap sort algorithm, very simple. Actually percolate down. Let's see, let's do one of these. Okay. Heapify into a max heap. Um, let me see the heapify operation again. Okay, it starts with this one and it makes sure that this thing is a heap. So there may be some exchanges. Then it makes sure this is a heap. Then it makes sure this is a heap. Okay, so that's how it works. So let's go back to here. It's gonna, this is the root. This is the left child of the root. This is the right child of the root. This is the left child of 63. This is the right child of 63. This is the left child of 95, and this is the right child of 95. So these are all leaves, and so this is the first inside node, and so we have to heapify this with this is the parent, and this is a child, and this is the child. So it looks like this is fine. And this one now, we have to heapify this one. This children is 50, 37, 80, 82. Okay, so that the 82 and the 63 have to exchange because 82 is a child of 63 and 82 is larger than 63. So 82 and 63 exchange. So now we've got, so 70, 60, 60, I'm gonna first copy this down here. 95, 37, 82, 55. Okay, so that's 1, 2, 3, 4, 5, 6. Okay, so I said that 63, the children of 63 are 82 and 50, and 82 and 63 have to exchange places. So 82, this becomes 63, and 82 goes right here. Okay, so now we have, so now 82, yeah, 82, 37, and 63 is a heap. 95, 50, and 25 is a heap. But 70 is the parent of 82 and 95. Well, that's not good. So we have to exchange 70 with the larger of its children, and that would be 95. So I'm going to take 95 and I'm going to cut that out and put 70, and I'm going to put 95 up here. Okay. So now 95 is bigger than 82 and 70. 82 is bigger than 37 and 63. And 70 is bigger than 50 and 25. Okay, so that's my heapified. I've heapified this into a max heap. Let's see if it's right. Yep, very good. Okay, you can do the rest of it. Tell you what, I'll do one more time. So we have time. Okay, so what's this one? Number 2. Heap sort has heapified into an array that, okay, and is about to start the second loop. Oh, heap sort. Heap sort is just and it's about to start the second. Oh, it's about to start the second for loop. Okay. What is the array after the first iteration of the second for loop? All right. Well, what is the second for loop? This is the second for loop. So okay, the first, this thing heapifies it. And then the second for loop starts with I pointing to the very last. Okay, so this is a for loop that starts at the last index all the way down to the 0th index, decrementing each time, swapping the root node with that I, and then percolating down that new root. You know, it took the okay, so after the first iteration of the array, it's just heapified it. Now after the first iteration, what is the array after the first iteration of the second loop? Okay, so this is so I'm going to put the heapified array in here. This is a tough one. 30, 56, 16, 23, 55, 39. Okay, so this is the recently heapified array. Let's see. 76 is bigger than 30 and 56. 30 is bigger than 16 and 23. 56 is bigger than 55 and 39. So the first thing it's going to do is it's going to swap after the first iteration of the second loop. So it's going to swap 39 and 76. 76, 39. And then it has to percolate down. So 39 is bigger than 30, but not bigger than 56. So 56 gets exchanged with 39. And then 39 has to look at its children, and that's 55 and 76 are 39's. No, not 76. 76 is gone. I wonder if I should leave 76 or anyway. 55 is the only child because 76 is not. It's like it's not there. Remember, the index has moved up. This is the one that was just pulled off the top. So we don't heap this. If we were to heapify this, this would get right back up to the top again. That's not what we want. So 39's only has one child, and that's 55. And so that has to be exchanged. So this is going to be 39 right here. And 55 is going to go here. Is that right? Yeah. So it's like this is not there, but these are now there. Now, I wonder if this is part of the answer or not. Am I supposed to take that off the answer or not? Well, I'm going to see. Check. Oh, good. So yes, I do. You do leave this there. Let's see what the next one looks like. Okay. Heap sort has heapified an array to that. We see that this is bigger than these two, and this is bigger than these two. And it's about to start the second. It's about to start the second for loop. Okay, second for loop is where we start to do the sort. We pop this bugger off, we exchange it with this, and 31 ends up here, and we percolate it down, exchanging it with this, 31 is exchanging it with this. That's what's going to happen. Okay, what is the array after each loop iteration? Oh, after each loop iteration. Okay, so let's start with 78, 69, 58, 32, 31. Okay, so this is how it starts out. And the second loop is going to exchange 31 and 78. Yes. So I'm going to take this off of here, put 78 here, and put the 31 here. And then we have to percolate this down. And so this is both children are bigger. So I got to take the bigger of them, take the 69 and replace that with 31. And the 69 goes right here. And so then we have, so 69 is bigger than 31 and 58. 78 is not part of the equation anymore. So 31 only has one child, and that's 32. 32 is bigger than 31, so we should exchange those two. This is 31, and 32 is going to go here. So this is what it looks like after the first iteration. I think this should go down here. And that's after the first iteration. I hope this is right. And then let's do the second one now. So now we're gonna pop off the 69 and we're gonna put it where the 31 is. So I'm gonna pop off the 69 and put it where the 31 is. Right. And so now it's 31, 32, and these don't count. So it's just these three. Is 31 bigger than its no, both its children are bigger. So 58 is the bigger one. So I take the 58 and exchange it with the 31. And and so we're only dealing with these two or these three because these are out of the equation. Okay, so now what's next? Let's copy this up. And we're gonna pop off the 58 and we're gonna exchange it with the 31. So let's pop off the 58 and exchange it with the 31. And then we have to percolate that down. These are out of the equation, so it's only these two. This is the root and this is the left child. It's out of order, so we got to exchange these two, and we end up with 32 here and the 31 here. And that's okay. Then we're done with this iteration because these are out of the picture. This is the root, this is the left child, and it's a heap. And so now the last iteration is this one here. Let's copy this and put it here. And so it's only these two that we're dealing with. This is the last one. We cut this off and we exchange it with this one. 32 is here. And we well, anyway, that's it. Now we're done because these are out of the picture now. and all we have left is the 31. That's it. So I think this is it. And this is sorted. All right, I'm gonna see if this is right. Each incorrect answer is highlighted. Oh, I'm sorry. These are not iterations. These are I, and I goes from a bigger one. Where's the I starts up at the max and goes down. So I goes 4, 3, 2, 1. So this should have been up here. So I got them out of order. See, I got them out of order. This one is what I had for number 4. And this is the first one, which I put here, see. All right, so anyway, now you know how to do it. You can go ahead and do the next one. So you can do this one. Perfect. All right, so this is the Python version of the heap sort. Oh my gosh, are we past time? I believe we are. 3:15 to 4:15. Okay, so this is the Python heap sort. Go through. We just did it. We just basically did this. This is the Python version. Is this what I'm going to have you implement? No, I'm not going to have you implement this. Not this time. Later on. And this is the priority queue abstract data type. And I want you to look at this because this is what I'm going to have you implement in the next assignment. And basically, you use a heap to maintain this priority queue, because the priority queue, you're only looking at the top one, pull that off, and then it be heaps where we're going to be looking at a min heap because it's the lowest one has the highest priority. And so that explains this. There's a payload with each node. And so I'm going to have you implement that, something, a person's name or some information. And then I'm going to have you implement these methods that go along with the priority queue. So it's just a type of list, just like a you know, a stack, a queue, a deque, a priority queue, and heaps is the absolute best way to implement a priority queue. All the worst operations are log n, and the rest of them are O of 1. So treeps are, I want you to go through here and do these exercises. Treeps are very interesting. It's a way of combining both a binary search tree with a heap. And so first, you, like inserting a node, first you insert it as though it's a binary search tree, but then you give it a random index, and then you reheap you reheap it based on that random index, and it pretty much mostly maintains a full binary tree structure, whereas a binary search tree can kind of get, you know, a lot of empty branches, and it can get inefficient. By the height can get large, even though there's not a lot of nodes. This is a way of keeping that from happening. And the thing about it is when you are reheaping, when you are inserting, and you are percolating up, you aren't really, the swap doesn't work. It's got to be a rotation. And remember, we learned about rotations in binary search trees. And so it's a little bit, the algorithm is a little bit more complex to be able to get this added efficiency of a full binary tree, but you got to do this rotate with rotation at the parent, and you may recall that from AVL trees before. It's kind of complicated. interesting. I'd love to give you this as an assignment in Python, but I'm not going to. But go through these exercises so you understand the concept. All right, well, that's all I have for today, and I will see you tomorrow. Thanks for watching.